Alright guys, today we are starting Chapter 3. Chapter 3 is when calculus starts to get really interesting. Not that limits were not interesting before, but limits can be a little tedious, and so can derivatives, but derivatives have a lot of nice, neat applications. So all of that stuff we've been talking about with limits, how to find limits analytically, maybe graphically or by a table, numerically, that's all going to inform Chapter 3, especially the first section of Chapter 3. So let's dive right in. We're going to talk about the tangent line problem and introduce derivatives. So the things we're going to do today, we're going to learn how to find the slope of a tangent line to a curve at a certain point. Specifically, we're going to use the limit definition of a derivative. We have two different limit definitions. We're going to use those two limit definitions to find the slope of a tangent line at a curve, at a certain point, that is. We're also going to talk about differentiability and continuity. Okay, let's dive right in. As we've discussed before, there are several problems that calculus solves. Here, broadly speaking, 4 of them. You have the tangent line problem, velocity and acceleration problem, the maximum and minimum problem, and the area problem. And calculus solves each of these. Now, number 4 here, we won't get to this until Chapter 5. The area problem, that'll be solved by integral calculus. The first 3, however, we will solve these with differential calculus, and that's where we're going to start today. Okay. The first thing we want to talk about is tangent lines. And I guess before we talk about finding slopes of tangent lines, we need to talk about what a tangent line is. But a tangent line can be defined in many different ways. Here we could say that a tangent line is that line that intersects a circle at exactly one point and is perpendicular to the radius, the radial line, as we have this picture here. Now, we aren't going to really deal with circles for the most part because typically we'll be dealing with functions in this class, and we all know that a circle doesn't pass the vertical line test, so it is not a function. We will deal with what are called implicit functions a little later on, but usually we're going to talk about explicitly defined functions. Now, a few more examples of a tangent line. We could talk about a tangent line, say, being a line that intersects a curve at point P and is only on one side of that curve. See, this line here is all above the curve. That would be maybe one potential definition. Maybe another definition would be a line that intersects a curve at exactly one point. So see here, the definition of not staying on one side of the curve doesn't really apply here because that tangent line, that blue tangent line, is on both sides of that curve, but it only intersects once. And this third situation here, we could say that a tangent line, if we're working with the definition that a tangent line is a line that just barely touches a curve at a single point, that definition doesn't really hold up here because if you extend this tangent line, notice it intersects over here, so it's like a secant line at that point. But I think a good working definition for us, however, would be that a tangent line is a line that intersects a curve at one point in a given neighborhood of x. For instance, if I look at point P here and look at the x value where point P is, the x coordinate, right where the cursor is, if I say that that blue line is tangent and it only intersects the curve where the x values of my cursor is, I could say like that's a little neighborhood of x. There's an open interval of x values right where my cursor is, such that in those x values, as far as those x values are concerned, the blue line does not intersect the curve more than once. I think that's a pretty decent definition to work off of. So a tangent line, we can say, is a line that intersects a curve at exactly one point, at least on some neighborhood of x, in some small interval of x, however small we want to define it, or maybe as big as we want to define it, that it only intersects a curve at exactly one point. Okay? But it boils down to essentially, why we want to find the tangent line is because at that point, at point P, for instance, on this previous page, at point P, the slope of the tangent line is equal to the slope of the curve. That's why we want the tangent line. Because at this point P right here, the slope of the curve is equal to the slope of the tangent line. At this point P here, the slope of the curve is equal to the slope of the tangent line. So what we want are slopes of curves. And the way we're going to find slopes of curves is by finding the slopes of the tangent lines at the points we're concerned with. Okay? Now, let's see here. We talked about this in a previous video, in previous lectures. In fact, in section 2.1, we talked about one way to approximate a tangent line would be to look at secant lines. That is, if we have a point on a curve, C, f of C. That's just an x, y value. And then we look at some small distance away from C, say C plus delta x. So we have an x value right here where the cursor is. It's C plus delta x. And then you look at that point, let's say P and Q. And you want to find, say, the slope of that line. Well, we could use just the regular slope formula. M equals y2 minus y1 divided by x2 minus x1. And if you take that expression for slope and then take the limit as delta x gets smaller, smaller, as you take that limit as x goes to 0, you'll wind up with the slope of the tangent line. And now you see why we have been dealing with limits, because what we're going to do here is take the limit as this expression goes to 0. That's called a difference quotient. A lot of college algebra and pre-calc books are introducing difference quotients in the sections on functions. So you might have seen these before. So again, let's just reiterate where this comes from. This is just a point. C plus delta x, that's an x value. F of C plus delta x, that's a y value. Here, C is an x value, F of C is a y value. So we have, let's call it a point P and a point Q. If we want to find the slope of the line that connects P and Q, just apply the slope formula, and we get, if we call this x1 and y1, and this x2 and y2, we have the expression f of c plus delta x minus f of c divided by the difference in your x values, c plus delta x minus c. And then one minor step here is just to simplify the denominator. Since we have a negative c and a positive c, that leaves just a delta x on the denominator. Again, this is just an algebraic move here. It is using the slope formula with these two abstract points. Okay? And then where the calculus comes in is when we take the limit of this expression, the limit of the difference quotient. Because if you recall, let's take a look at, just to refresh everybody's memory, let's take a look. So let's think about this. So here we have a curve. This curve right here is f of x equals sine x. Okay, now let me show you the tangent line at point O, at this point right here. So right now what we are concerned with is the tangent line at this purple point. Okay, so we have the red curve, that's sine of x, and we have this purple line, that's the tangent line. Now, we don't know how to find that specifically just yet, but here is what we're doing. Just to refresh your memory from a few sections ago. The way we approximate that purple tangent line is to draw a secant line. So here I have a green secant line. Let's say that point's just way over there. You see how that secant line is not a very good approximation of that purple tangent line? So the green line and the purple line, they both have a positive slope. They're both, increasing. They're both rising from left to right. but they're not super similar. But notice what happens as I make those points closer and closer together. So right now, look at this h. H right here, that's the distance between the green point and the purple point. We call that delta x usually. Some books call it h, but our book calls it delta h. Excuse me, delta x. So as I decrease delta x, that is decrease h, I get a better and better approximation of my tangent line. Notice the green line is getting more similar to the purple line. That is, my secant line gets to be a better approximation of my tangent line. And notice I have h, which is delta x equals negative 0.1 right now, and as it gets closer to 0, they're actually the same. Look what happens is if I make h go a little bit bigger in the positive direction. Again, those two lines, my green secant and my purple tangent, look nothing alike. One has a positive slope, one has a negative slope. But again, so h equals 2 right now. But as h, that is delta x, gets smaller and smaller, they become more similar until as h gets to be 0, as the limit approaches 0, they're actually the same. The secant line and the tangent line coincide. So that's why we've been talking about this idea of limits as far as how it informs our discussion of differential calculus. We're going to take the limit of a difference quotient, at least to start with, the limits of a difference quotient, and that's how we're going to find derivatives. Okay? So this definition right here is how we are going to find derivatives to start with. So let's look at a couple of examples. Let's start off easy. Let's find the slope of the tangent line to this linear function at this point C. So essentially we want to find the slope of the tangent line at this C value. Remember, C's are x values. At this x value, we want to find the slope of the tangent line at this function. Now this is a linear function. So it turns out a linear function is going to coincide with its tangent line. They're going to be the exact same thing. Now let's take a look at why that might be. Okay, so we want to find the slope of f at c equals 2. So let's dive right in here. Okay, we have f of x equals 2x minus 3 and c equals 2. Okay. Now, what was our definition? Our definition was that the slope of the tangent line, so let's call it like m sub tan, equals the limit as delta x goes to 0 of the difference quotient f of x, we use c's here, c plus delta x minus f of c all over delta x. Now let's apply this limit definition to this function. So we can say that the slope of the tangent line we're concerned with is equal to the limit as delta x approaches 0 of our difference quotient. Now let's apply just some algebra here. We have f at c plus delta x. So we take c plus delta x and plug it into our function, where c is 2. So that's 2 evaluated at 2 plus delta x. So notice here, that is f of x evaluated at c plus delta x. So 2 plus delta x is c plus delta x minus 3. But on the numerator of our difference quotient, we also have minus f of c. So minus 2 times 2 minus 3. Okay, that is f of c. Just plug in, substitute in 2 into our function. Now it's very important to properly use parentheses here because we're subtracting off this value. Okay, now we have f of c plus delta x minus f of c over delta x. Now we want to find this limit, but can we use direct substitution right now? Well, I don't think so. If we try to use direct substitution to evaluate this limit, we'll produce a 0 on the denominator, which is not good. We can't do that, so we need to do some rearranging first. So remember to use your proper limit notation. So equals the limit as delta x approaches 0. Now we're still going to have a delta x on the bottom. What about the top? We have 2 times 2 is 4. Let's see, 2 times delta x is so plus 2 delta x minus 3. Then what's this right here? That's 2 times 2 is 4, minus 3 is 1, so minus 1. So I think you can see we're going to have a nice cancellation out there on the numerator because we have 4 minus 3 minus 1, so that's 4 negative 4. So we're left with 2 delta x over delta x, which just ends up being the limit as delta x approaches 0 of what? Of 2, because the delta x's divide out. Now remember, this is a constant function. What's the limit of a constant function? Here, delta x is going to 0, but there's no delta x's left in our function. That's a constant function. It's a horizontal line at y equals 2. So the limit, in fact, as delta x approaches anything you like, is 2. So the slope of our tangent line at x equal 2, that is c equal 2, is 2. Now why does that make perfectly good sense? Because this is a linear function. What do we know the slope is? Well, we know the slope is 2 and the y-intercept is 3. Okay? Because this is in y equals mx plus b, slope-intercept form. So we knew the slope was 2. So we found the slope of the function at x equals 2, and we found that it was exactly what we thought it should be. Okay, so we just use calculus to find a very trivial slope. We could have found that slope using the slope definition that we've been using since junior high, since algebra. Okay, since you first encountered algebra and graphs, in junior high or high school. Okay, but the calculus verifies what we have already known. Okay, so again, what we did here was we found the slope of the tangent line to this function. It's not a curve; it's a straight line, and it turns out that the slope is 2, and in fact, here's something a little neat for you. It doesn't matter what c equals here. C could have equaled anything else we wanted it to be. Let's just, for the heck of it, say c equals let's say -1. Let's do the exact same thing over. Okay, we could say the slope of the tangent line equals the limit as delta x approaches 0. And now let's apply the definition again. Okay, it's f at c plus delta x. So that's 2 at -1 plus delta x minus 3 minus f of c. So that's 2 times -1. Oh, fix that. -1 minus 3 all over delta x. So let's do some rearranging here, just like before. We still have a delta x on the denominator. Now we have 2 times -1, so that's -2. We have 2 times delta x, so plus 2 delta x minus 3. And then we have, let's see here, we have negative 1 times 2, that's negative 2, minus 3, that's negative 5, but we have negative 5 minus negative 5, so that's plus 5, equals the limit as delta x approaches 0. And what's left over? Well, we have 5 minus 3 minus 2, so that's just 2 delta x left over delta x on the bottom. And now we have our exact same situation happen. We have the limit as delta x approaches 0 of 2 equals 2. See how that didn't matter what c was. Now, let me be clear. That only works here because this is a linear function, and the linear function is going to have the same slope everywhere. The slope doesn't change in a linear function. In general, when we're talking about different curves, the slope is going to be different at every different point. Excuse me, I shouldn't say that. The slope is usually going to be different at your different x values. Now, you might have a curve, say like this, where the slope here and here of those tangent lines is the same. But in general, if you just pick two random points, you're not going to have the same slope unless you're dealing with a linear function. But you will have slopes repeat if you have some sort of periodic behavior, or just depending on what your function is. So, but because we have a linear function, the slope is the same at all values of c, which remember, c values are x values. Just like when we were dealing with limits, c is an x value, a specific x value, and same thing here with derivatives. C is a specific x value. Okay, let's see what we have here. Let's look at another example. To find the slope of the graph of f of x equals x squared plus 1 at two different points. Let's say we want to find the slope at the point 1, 2 and negative 1, 2. Now, we could apply the previous definition twice, where c equals 1 and c equals negative 1. Or it might be convenient to let c be arbitrary. That is, just let c remain c in the limit definition. And then once we are all done with our limit, presumably there'll be a c left over, and then we can substitute in the different values of c. So let's see what happens. Okay, let's see here. I keep saying we have c's, and I keep saying let's see here. We have the function f of x equals x squared plus 1. Now, we want slope at x equal 1 and x equal negative 1. Okay, that was the point 1, 2 and negative 1, 2. So we want the slope at those 2 points. So let's apply our definition. So remember, our definition is the limit as delta x approaches 0 of the difference quotient f of c plus delta x minus f of c over delta x. Okay, now let's apply here, but let's not use x equal 1 for c and negative 1. If we did that, we would have to use this definition and find two specific limits. Let's just let c remain a variable and watch what happens. So limit as delta x approaches 0. So let's just evaluate this function at c plus delta x. So that would be c plus delta x squared plus 1. That's f of c plus delta x. Minus, f of x, which is x squared minus 1. Make sure don't forget those parentheses like I almost just did there. All over delta x. So we have f of c plus delta x. That's this term and that term. And then we have minus f of x. Now let's just simplify. Now we have a c there, sure, but don't worry about that. So let's see. Limit as delta x approaches 0. Now we're going to have a delta x still hanging out there on the bottom. Let's figure out what's going on here. So we have, let's see, c squared plus 2c delta x. Okay. Plus delta x squared plus 1. That's just me evaluating this first half of the numerator. And then minus x squared minus 1. Oh, you know what? I messed up right here. I forgot to evaluate this. This is f of c, not f of x. So let me go back and fix this real fast. That should be a c there. Sorry about that. I was about to say this is not going to work out how I need it to work out. Because that's f of c, not f of x. Okay? In my definition here, it's f of c plus delta x minus f of c. We're going to eventually use x's here, not c's. That's why I made the mistake there. But we're good now. Now notice what happens to this big, nasty limit. A lot of stuff is about to add to 0. So we have the limit as delta x approaches 0. There's still a delta x on the bottom, but look, see what happens here. Those go. Negative c squared, positive c squared. Plus 1, minus 1. Now here's the way you know if you've probably done this right. Is if the only thing left over are items, terms that have a delta x in them. Notice the only two terms left over have a delta x. Let's factor out that delta x, and we have, let's see, 2c left over there, plus delta x. Okay, limit as delta x approaches 0. We can divide out that, leaving us with, oh, not a fraction. Sorry, divide that out, leaving us with 2c plus delta x. And what is the limit as delta x goes to 0? Well, this is a nice linear function. Now, all we have to do is directly substitute for delta x, let it equal to 0, and we have 2c plus 0 equals 2c. Okay, so our slope of this function is given by 2c, where c is whatever value we want it to be. Okay, so if we want, say, the slope at this point, let c equal 1. So m equals 2c, where c again is an x value. So slope at x, or let's just call it c to be consistent, c equals 1 is 2 times 1 equals 2. Slope at c equals negative 1, that is 2 times negative 1 equals negative 2. Okay, so notice here we didn't have to do the limit definition twice. If I had substituted in c equals 1 here, and so instead of these c's I'll just have a 1, the arithmetic and algebra would have been marginally easier, not much. You just, because people, a lot of students see, c's and see different letters and think things are harder. It's the exact same process, but sometimes it's superficially easier if there's just a number there instead of a variable. But we would have had to apply the limit definition twice, once for x equal 1, once for x equal negative 1, or c equals 1 and c equals negative 1. But here, since we let c be a variable and didn't specify that it had to equal this number or that number, then when we got our solution down here, when we evaluated the limit, we got a function. And that's what we're going to go to next, is we're going to stop evaluating, most of the time at least, at a specific value of x. So stop evaluating at c equals this or c equals that. Find the general derivative function first, and then evaluate at specific x values or c values. Okay, so notice here, this is a function. Also notice, this is a what type of function? Quadratic, and this is a linear function. So that's going to be a nice relationship. When you take the derivative of a quadratic function, you're going to get a linear function. When you take the derivative of a cubic function, you're going to get a quadratic function. Now, can you guess what type of function the derivative of a quadratic is going to be? Excuse me, a linear is going to be? The graph, the derivative function of a linear function is a constant function. So you're reducing the power of the leading coefficient by 1 each time. You're reducing the degree of the polynomial each time. And this is going to be true when we're taking derivatives of polynomials. Let's say you want the equation of the tangent line. So what about equation of tangent line at, let's just pick one of them, x equal 1. So a lot of the work we're going to do in Chapter 3 will be about finding the equations of tangent lines. Okay? So if we want to find the equation of the tangent line at x equal 1, well, first of all, we need a point and we need a slope to use point-slope form. Remember, point-slope form is y minus y1 equals m times x minus x1. So what is our y value here? Well, our y value is 2. We were given that in this case. A lot of times we won't be given the y value, so we will have to go to our original function to find the y value here. But so we have the point 1, 2, and m equals, we said, 2. So apply the point-slope form. This right here is called point-slope form. So y minus y1 equals m, which is 2 times x minus x1. Oh, x minus x1 being 1 here. Now let's clean this up. Let's put this in point-slope form. So y equals 2x minus 2 plus 2, or y equals 2x. So here is the equation of the tangent line of this function at this point. Okay? And that's going to be a lot of what we're doing in this chapter. In fact, for the next several weeks, well into Chapter 4 as well. So let's take a look at this. Let's make sure I'm right. So we have x squared plus 1 is our function, and y equals 2x is our tangent line at x equal 1. So x squared plus 1, there is our function. Let's plot the point 1, 2. So there's the point where we wanted to find our tangent line, and let's see if y equals 2x looks like a tangent line. Y equals 2x. There we are. I think we're good. Now, what do you think about that other point? The other point we were talking about was negative 1, 2. So there's the orange point. What would you suspect the slope of that line is, considering we know this, what do you think the equation of that line is, considering we know the equation of this green tangent line? Well, I think y equals negative 2x will do it. Remember, we found the slope to be negative 2, and if we apply the point-slope form, we would get that the, let's not do that. That caps lock looks bad. We would get the equation equals y equals negative 2x. So there are the two tangent lines for those two slopes that I found. Again, the tangent line, let's just imagine zooming in. Zooming in, if we could zoom in further and further, you know, we are so close here, and it's always, if we could just keep zooming in. Now this is even having trouble rendering it because it looks like they're meeting at many, many points, but they're only touching at one point. The tangent line and the curve x squared plus 1 are only touching at a single point. Again, it's hard for the software even to render that happening because you would have to zoom in infinitesimally to see that. But that's what a tangent line is. Okay? So let's do a little more work. Let's figure out some different scenarios. What other kind of neat things happen with tangent lines? Okay. What about if you take a limit and you get an infinite limit? So you set up your difference quotient. You take the limit as delta x goes to 0. What about if you get positive infinity or negative infinity? Turns out that's going to be a vertical tangent line. Okay, so you set up a difference quotient, you take the limit, and if it turns out to be an infinite limit, that means there is a vertical tangent line at that point. Okay? So let's see here. Vertical tangent lines sometimes happen like right there at this particular point. That's called an inflection point. And a vertical tangent line occurs right there. Okay. And just to give you a little preview, an inflection point is when a graph, the concavity of a graph changes. So this graph to the left of C is kind of like opening upwards. If you think about like a parabola, it's opening upwards. And then to the right of C, it's kind of opening downwards. So the concavity changes there, and in this case, we get a vertical tangent line. Okay, and so that's what the case is going to be if you use the limit definition and the limit ends up being either positive or negative infinity. So let's look at a nice example. Okay, so we have the function the cubed root of x. So let's look and see what happens, what the slope of the tangent line, is. Now I'm going to go ahead and tell you we're going to get an infinite limit in this case, but let's just see why that happens. Let's see here. So our function is f of x equals the cubed root of x. Now we were specifically talking about c equals 0. So we want to find the slope of the tangent line when c, that is x, equals 0. So let's apply the definition. The limit definition says we take the limit as delta x approaches 0 of the difference quotient. Okay, now it's f of c plus delta x. Okay, so that's going to be the cubed root of 0 plus delta x minus f of 0. So that's the cubed root of 0. Okay. So we have the f of c plus delta x minus f of c over delta x. Okay, let's see what happens here. Equals the limit as delta x approaches 0. So we have a delta x on the bottom. Now, the cube root of 0 is just 0, so that there's nothing there. What do we have here? The cube root of 0 plus delta x is just the cube root of delta x. Okay, well, let me fix that, make it a little better. The cubed root of delta x. Okay, now, in order to see what's going on here, we need to remember our rules of exponents. Just off to the side here, delta x, the cubed root of, that's equal to delta x to the 1/3 power. Now, if we have the cubed root of delta x over delta x, that's delta x to the 1st power. Now, think about how we can rewrite that. That is delta x to this minus 1, so that's the negative 2/3 power, which equals 1 over delta x raised to the 2/3 power. So equals the limit as delta x goes to 0 of 1 over delta x raised to the 2/3 power. Now, we have to think about what's going on with this limit. We could make a table if we wanted to. There's nothing wrong with that, but we can just rationalize through what's going on here. If numbers are getting closer and closer to 0, because delta x is getting closer and closer to 0, so that's going to be very small values. What happens when you square a very small value? Say we square 1 over 10, 1/10. When you square 1/10, you get 1 over 100, an even smaller number, a much smaller number. If you square 1 over 15, you get 1 over 225, a much smaller number. So you square a small number, then take the cube root. Now the cube root does make it not as small here, but it's still getting to be very, very small numbers on the bottom. As x gets closer and closer to 0, the denominator gets very, very, very small very quickly. Okay, so when I take 1 and divide by smaller and smaller numbers, what happens? Well, if you take a constant and divide by smaller and smaller numbers, then the result is just bigger and bigger numbers. Think about it like this. If I do 1 divided by 1/2, that's equal to 2, right? If I do 1 divided by 1/5, that equal to 5, right? If I do 1 divided by 1 over 100, that's 100. If I do 1 over 1,000, that's equal to 1,000. So as the denominator is getting smaller, the entire expression here is getting much bigger. So that limit is equal to positive infinity. Thus, there is a vertical tangent line at x equal 0. Okay? So if you're working through some of these limits and you end up getting a infinite limit, whether that's positive infinity like here or maybe negative infinity, that means you have run into a vertical tangent line. Okay? We need to talk about the general derivative. So instead of finding derivatives at specific points, let's use our definition to find a derivative function, and then later on we'll evaluate its specific values, much like we did with that function x squared plus 1, where we let c be a variable, and then we went back and substituted in the values of c we were interested in. Let's see here. So this is going to be our working definition for the derivative of a function. Notice there's no c's here, otherwise it's exactly the same. So we say f prime is equal to the limit of the difference quotient, f of x plus delta x minus f of x over delta x. Okay, so we're not going to worry about necessarily any specific c value in this definition. We're going to first always find a derivative function, and then if we want to later on find a specific slope at a specific value of x, we can simply evaluate our derivative function at that x value we're interested in. So let's see here. Very important. The derivative function, the derivative of a function is also a function. That's very important. You take the derivative of some given function, you get a function. You can graph it. You can do all kinds of stuff with it. You can take a derivative of a derivative. Okay, there's all kinds of stuff we're going to do with these derivative functions. We're going to do lots of graphing specifically. Now let's talk about a few terms here. If the process of taking a derivative is called differentiation. If you can take a derivative, a function is called differentiable. So it turns out there's going to be some requirements for if you can take a derivative. For instance, we're going to talk about that soon, continuity and some other things. Okay, but if a function if you can take the derivative, it's called differentiable. And if you can take the derivative over a certain interval, then we say it's differentiable on the open interval a to b. Okay, or maybe it's differentiable over the entire real number line. Many functions will be, not all. So we have those three words here: differentiable, differentiation, finding a derivative, and then finally differentiable on an open interval. So just make sure you understand what those different words mean. Differentiable at a point versus differentiable on an open interval versus differentiation versus the derivative, that kind of stuff. Now, we have, because calculus was developed independently by different folks on different continents, in different countries at least, we have a lot of different notations. So these are all notations you're going to see. These first two might be the most popular, f prime of x for a derivative, or maybe dy over dx. But we're going to use y prime. We're going to use all these, at least some. So whenever you see these notations, just think, okay, we're taking a derivative. Okay. This is pronounced dy over dx. This is pronounced y prime. We say d dx a lot, or maybe just dx. Okay, again, these are all notations for a derivative. F prime of x is probably the most common, though. But we'll use all of these in this class. Okay, let's see here. Let's up the ante a little bit. So we have a cubic equation. So we want to find the derivative of f of x equals x cubed plus 2x using the limit definition. So x cubed plus 2x. Now, we don't want to find a specific slope. Here we're looking for the general derivative function. So x cubed plus 2, so we had f of x equals x cubed plus 2x. Again, we're not looking for a specific slope here. We're looking for the derivative function. So we can say that f prime of x, that is the derivative function, is equal to the limit as delta x approaches 0 of f at x plus delta x. So here's our new working definition. The limit as delta x approaches 0 of f x plus delta x minus f of x over delta x. So there's our working definition. And so this is going to take a little bit of work here, a lot of algebra. So let's see here. F of x plus delta x. So that is x plus delta x cubed plus 2 times x plus delta x. So that's f at x plus delta x minus f of x. So x cubed plus 2x all over delta x. Now I'm going to have to expand that numerator and simplify because I can't use direct substitution immediately. If I try to use direct substitution, I'm going to get a 0 on a denominator, which is no good. Now let's do some scratch work off to the side. What's x plus delta x cubed? Okay, let's see. X plus delta x cubed is x plus delta x times x plus delta x times x plus delta x. X plus delta x cubed. Let's take two of those at a time. Let's take the first two. Okay, that is x squared o plus 2x delta x plus delta x squared times x plus delta x. Be really careful here. There's a lot of algebra in this one. Okay, I need some more room here. Equals, okay, I have x squared times x, that's x cubed. Then I have x squared times delta x, so that is plus x squared times delta x. I then have 2x delta x times x, so that's plus 2x squared delta x. I then have plus delta x, let's see, x cubed, I lost my place here, x cubed plus x squared delta x. Yes, plus 2x delta x is 2x squared delta x, yes, plus 2x delta x squared. Okay, I'm losing my spot here. Too far away from the screen. Okay, then I have delta x squared times x. And then I have delta x squared times delta x, so plus delta x cubed. All right, that was a lot. Now, hopefully I've not made a mistake there. Again, I'm kind of far away from the screen and my handwriting is challenging on this tablet. So I have x cubed. Do I have any like terms here? Okay, I take care of that one. I have x squared delta x. Do I have any more x squared delta x's? Do I have x squared delta x? Looks like I have 3x squared delta x's. Okay, x squared delta x's. So I have one right here, x squared delta x, and delta x. That's plus 3x squared delta x. Okay, then I have 2x delta x squared. So I have 2x delta x squared. And then I have delta x squared x. Okay, so I have plus 3x delta x squared. So plus 3x delta x squared. Okay, that takes care of that one, and then plus delta x cubed. Whew. Okay, I think that's right. Oh no, that's not right, because I have to subtract off minus x cubed minus 2x. Okay, now what happens here? Okay, equals the limit as delta x approaches 0. Okay, let's see here. I have x cubed, and then I have a 2x over here. What's going to happen with that 2x? Oh, I missed a part. Okay, I made a mistake, guys. Again, I made a mistake here. Right here, I did this and put it right here. I forgot to do 2x plus 2x plus 2 delta x. So sorry, I need to annotate that. Okay, like right here, after this, right here, should go this distributed right here. 2x plus 2 delta x. Now, why is that important? I knew there was a mistake because that has to cancel with that. Because all these terms left over have to have a delta x in them. Okay. So what's left over? And I can't forget about that one. So I have let's see, plus. Or I just have like 3 x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all over delta x. Now, I need to factor that numerator, and this is the general process here. Simplify and factor. So if I factor out a delta x, that's the only thing they all have in common. They don't all have an x in common, but they all have a delta x in common. I'm left with a 3x squared plus 3x times delta x plus delta x squared plus 2 all over delta x. So now those delta x's are going to divide out. And what are we going to be left with? So that divides out and that divide out. We're left with 3x squared plus 3x times delta x plus delta x squared plus 2. Now let's finally take that limit via substitution. Okay, we're going to plug in a 0, substitute a 0 everywhere there's a delta x. So this is 3x squared because there's no delta x's there. Okay, plus, all right, 3x times delta x, so 3x times 0 plus 0 squared plus 2. So that term goes to 0, that term goes to 0, and we're left with 3x squared plus 2. Now, that took a whole lot of algebra, and I almost messed up there. Again, I've been doing this for a while, so I can kind of see when I made a mistake. You're going to have to be looking for that same stuff, and the only way that you get that little bit of intuition is by practicing a whole lot. Okay, so you know that if you're getting here and it doesn't look like things are canceling out, you've made a mistake somewhere, because everything has to cancel out that doesn't have a delta x left in it. And I noticed that I was about to have a negative 2x over here, and it wasn't going to cancel out. Thus, I had to backtrack and realize, oh, I forgot to distribute this guy right here, and so I kind of had to do it off the side and fix my mistake. Luckily, I didn't get too much further after making that little mistake. But we're all good now. So here is my derivative function. Remember how we talked about before? The derivative of a cubic is going to be a quadratic. Okay, you're going to reduce the degree by 1. You'll see why that is in a coming lecture. They'll make more sense in a bit. So here's the derivative function. Now, I can do things like say, what is slope at x equal, let's say, 0? That's f prime of 0. Well, f prime, let me label it back here. This is f prime of x. That's going to give me for any x value I plug in. Now this is defined for all real numbers. It's a quadratic. For any x value I plug in, it's going to give me the slope of my original curve at that point. So the slope of f at 0 is f prime of 0 equals 2. Slope at x equals 2. That's f prime of 2. And so that is 3 times 4 plus 2 equals 14. Slope at, so let's say, negative 3. That's f of negative 3. Sorry, f prime of negative 3. So that's, let's see, negative 3 squared is positive 9. Positive 9 times 3 is 27. 27 plus 2 is 29. So now we find this derivative function. We can find the slope of our original function at any point we want to, as long as the derivative function is defined. We can find the slope of any x value we wish. Okay, so this function we know is differentiable over the entire real number line because the derivative exists for all real numbers. Let's say that was a rational function, like with an x minus 2 on the bottom, or an x minus 5. Well, then the derivative wouldn't exist for all real numbers, so it wouldn't be differentiable everywhere. But this function, this nice polynomial, it's continuous everywhere, it's differentiable everywhere, and we can see that by looking at the derivative function. The derivative function is defined for all real numbers. Okay, so we use the limit definition, a whole bunch of algebra, we got the derivative function, and now with that derivative function, we can find the slope at any x value we please. We picked a few different points here. And this is going to be kind of like what we're going for the next little while. We want to find the slope function, the derivative function, not necessarily, we don't want to go through this entire limit process and only find one slope. That is, if we let c be a specific value. We just want to let c, in this case x, be arbitrary, so we get a derivative function and can then evaluate that derivative function at whatever value we choose. Now that we have talked about the original limit definition, we have a new alternative limit definition for a derivative. Okay. Now this one, typically we use this one when we want to find the derivative at a specific point. That's what it's used for. Now, again, we're typically going to want to use the prior formula because we can use that to find the general derivative of the function. But let's say we do want to find the derivative at a specific point. That is, we want to find the slope at a specific value of c, so a specific x value. Well, we have this we call alternative limit definition. I'll show you where it comes from. It's not so bad. Okay, so we have this new formulation of our derivative definition, f of x minus f of c over x minus c. Again, I'll show you where that comes from in just a moment. Now, we'll use it occasionally. It's not going to be our primary definition, but we will use this occasionally, and I'll show you why it might be useful here in just a moment. Let's just show you how it works, though. Let's find the slope of the square root of x at the point 4, 2. And then let's use our new alternative definition. So again, that's the limit as x approaches c of f of x minus f of c over x minus c. Alright guys, so we had the function f of x equals the square root of x, and we have the point 4, 2. We want to find the slope of the tangent line at 4, 2. Now, we have a new limit definition, new derivative definition involving limits. It is the limit as x approaches c of f of x minus f of c over x minus c. Okay, so we say that is equal to f prime at c. Okay, now, where does that come from? Just so we're going to hold off on the actual derivative for a moment. Where does this come from? Let me show you. Our original definition was as follows. The limit as delta x approaches 0 of f x plus delta x minus f of x over delta x. Okay? Now, how do we get this? Oh, sorry, I used the wrong, I need to use better notation here. F of c plus delta x minus f of c over delta x. Okay? Now, let's see how we can get this to work. It's not so bad. Let's do this. Set, let's see, x equal to c plus delta x. Okay? Now let's watch what happens here. So if we do that, we can say, okay, if x equals c plus delta x, then we can say this is the limit as, okay, we'll figure out where it's approaching first. It's f of x, just by substitution, minus f of c. Okay. Now, what's delta x? If x equals c plus delta x is x minus c, right? So delta x is x minus c. Here, I'll show you just the real fast. So this implies that delta x equals x minus c. So on the bottom, x minus c. Now, what happens if we take the limit as delta x goes to 0? That's the same thing as taking the limit as x goes to c. Okay? So that's where we get this little portion from. Okay, because as delta x goes to 0, x and c approximate each other. So again, this is where this comes from. Okay, the limit as x approaches c of f of x minus f of c over x minus c. Again, this is called the alternative definition. Alternative definition, whereas this one over here, I'll just call, for a lack of a better term, the regular definition. If I just say the limit definition of a derivative, this is what I mean. If I say the alternative definition, this is what I mean here. So let's go back and use the alternative limit definition. So we can say that f prime at 4, f prime at c, that's equal to f of x, so the square root of x, minus f of c, minus the square root of 4, over x minus c. Okay? So let's see here. This equals the square root of x minus 2 over x minus 4. Oh, I left off all of our limit definition, our limit notation. That's no good. Equals the limit, sorry about that, as x approaches 4 of f of x, square root of x, minus the square root of c over x minus 4. So this equals the limit as x approaches 4. Now, how did we solve these before? When we had roots involved, we had to usually rationalize the numerator to evaluate the limits. So let's do that here. We have the square root of x minus 2. Let's rationalize the numerator. So that's the square root of x plus 2. X minus 4. Now we have to multiply by the same thing on the top and bottom so as not to change the values of anything, equals the limit as x approaches 4. Now let's not expand the denominator. That's kind of a little trick here, not to expand the denominator. Just leave it factored. But what about the numerator? The numerator is going to be, okay, the two middle terms will cancel, add to 0. But the two outside terms will have x, the square root of x times the square root of x, leaving us as x. Then negative 2 times positive 2 minus 4. So notice here we have a nice cancellation happen. well, these cancel out, leaving us as 1 over the square root of x plus 2. And now that function is defined at x equal 4, so we can use direct substitution. Plug in a 4, we're going to get 1 over the square root of 4 plus 2. Oh, sorry about that. 4 plus 2 equals 1 over 2 plus 2 equals 1 over 4. Okay, so there we are. There's the slope of the tangent line at the point 4, 2 when our function is the square root of x. Okay, 1/4. So that was the alternative limit definition. Okay, let me stress this. The alternative limit definition is the context when we're going to use that is when we're trying to evaluate the derivative at a specific x value or a specific value of c. When we want a specific slope. If we don't want a specific slope, we're generally going to use the regular limit definition, because we can use that and it will result in just a derivative function, and we'll just typically that'll be the way we choose which one to use. If you want to find a general derivative function, that's probably we want to use this one up here, the regular one. If you want to find the derivative at a specific point, we'll usually use the alternative. Okay, and that's usually going to be the breakdown of that. Okay, but here's a good example of using the alternative limit definition. I will say, at least for my test, you will need to know both. Pretty soon here we will get some new ways to work with derivatives, and we won't even bother with the limit definitions anymore. But we will for the first couple sections, and it's very important when proving these newer, easier ways to take derivatives. But regardless, for the test, you will need to know how to use the alternative limit definition of a derivative and the regular limit definition of a derivative. Very important to be able to do both of those. Let's look at another example. We want to find the equation of the tangent line where f of t equals 2 over t at the point 1, 2. So we can apply our limit definition. Now notice, we only want the slope at one specific point, so we have an option. We can actually use the alternative limit definition if we want to, or we can use the regular limit definition and find a derivative function if we so choose. Okay? And here, since I specified the directions that I want to take that route for finding a derivative function, let's do that. So we want to use our regular limit definition. We'll find the derivative function. We will then evaluate that derivative function at t equal 1. That will be the tangent line slope we're looking for. And then we'll use the point slope form to finally write the equation of the tangent line. So f of t equals 2 over t at the point 1, 2. I guess we have f of t equals 2 over t, and we were interested in the equation of the tangent line at the point 2, 1. Okay, so let's see here. We can say that f prime of x equals the limit as delta x approaches 0. Remember, I'm using my regular limit definition here. It's delta x approaches 0. Okay, so I'm going to say f of x plus delta x. So that's 2 over, I should say t plus delta x, since we're a function of t, not x's. So f of t plus delta x minus f of t, so 2 over t over delta x. Now that's a nice rational function for us to deal with. When we have encountered limits of rational functions in the past, a good line of attack would be to first combine the numerator. So simplify the numerator first. Now I mean the numerator of that complex fraction. So the limit as delta x approaches 0. Let's see here. That's going to be 2t minus 2 times t plus delta x all over t times t plus delta x. Okay, let's see what happens here. Delta x is still in the bottom, at the very bottom that is. We have the limit as delta x approaches 0. Now how does that numerator simplify? We're going to have 2t minus 2t minus 2 delta x. So that the numerator of the numerator simplifies to negative 2 delta x. Now the denominator on the top half is just t times t plus delta x. And then we have a delta x like that. Now we need to divide that complex fraction. So we have the limit as delta x approaches 0 of, okay, now we have a fraction divided by another number, by another expression. So we're going to flip the divisor and multiply. So that's going to be, let's see, that's going to give us a negative 2 delta x on the top. Then that's going to give us a delta x times t times t plus delta x on the bottom. Again, what that does is that puts this delta x on the denominator. And I think what you see here is that a pretty nice division can be done, cancellation if you want to call it that, is that delta x and that delta x can cancel, leaving us with a negative 2 on the top, a t on the bottom, and a t plus delta x on the bottom. Now, I think we can take that limit now, because this function is defined when delta x equals 0. So we can directly substitute at this point, dropping our limit notation, and t plus 0, t plus 0 being t. So I think we can see here that our solution is negative 2 over t squared. Okay, so that is f prime at t. So this expression here will give us the slope of the tangent line at any value of t for which this function is defined. Now, f of t is not defined where? It's not defined for x equals 0. So we'll say that this function is not differentiable at the point x equals 0, because it's not defined at x equals 0. Notice it's not differentiable here either. So it's not continuous at t equals 0. It turns out not to be differentiable at t equals 0 because the derivative does not exist when t equals 0. We're going to talk a little bit more about differentiability and continuity in just a few minutes. Now let's continue on here. We want the slope of the tangent line at, we said, 2, 1. Okay, so we want to evaluate our function at this point. So we have the point 2, 1. Okay, so if we evaluate f of t, or excuse me, f prime of t at 2, that equals, let's see, negative 2 over 2 squared, so negative 2 over 4, so negative 1/2. So this is the slope of f of t at t equals 2. Okay, so if we want to write the equation of that tangent line, well, we could say, well, first of all, we need a point. Here's our point, 2 comma 1. Okay, here's our slope equals m, negative 1/2. We could write y minus y1, which is 1, equals m, which is negative 1/2, times x minus x1, which is 2. And we could say y equals negative 1/2 x, plus 1 plus 1. So y equals negative 1/2 x plus 2. Now, I guess I should be consistent here. This was a function of t. I should have been using t's right here. It's fine. It's not that big of a deal. Just be careful, like if you were entering this solution online, I bet it would want a t there because this was a function of t. Just be careful about the variable. This is the correct solution. Just be careful with how the functions are given as far as the variables used. Okay, so here's our tangent line. Now let's take a look at the graph. Let's see if that works. So here we want to graph this, and we want to graph this, and see if those looks like the correct tangent line. All right, so our function was 2 over t, or we'll just say 2 over x, and our derivative, our tangent line was negative 1/2 x plus 2, and that was at the point 2 comma 1. So does that look like the tangent line to you? I think it does. Okay, I think that works out nicely. What we did was, just to recap, we first found the derivative. We found the derivative of the red curve. Then we evaluated that derivative at the point in question, which was 2 comma 1. Now we only needed the x value to find the specific slope. So we plugged in a 2 for, I guess it was actually an x value, a t value. We plugged in a 2 for t. We got the slope. Then we used the point slope form to write the equation of the tangent line we were looking for. That's the equation of this blue line right here. Okay, that's going to be the process for a lot of the exercises we will be working on throughout this chapter. Now, let's talk about how differentiability and continuity are related. These two concepts are related pretty nicely. Let's see what we have here. The alternative limit definition of the derivative is pretty useful when we're talking about differentiability and continuity. Because if you look at this limit here, we have to guarantee that for that derivative to exist, that this limit has to exist. For this limit to exist, the right hand and the left hand limit have to be the exact same number. Remember when we talked about a left hand derivative and right hand derivative and a two-sided derivative, that a two-sided derivative did not exist unless the left hand and right hand derivative equaled the same finite number. Let's look at an example. Okay, we've talked about the step function before. The step function, or the greatest integer function, what it says is you take you find the function value by finding the greatest integer less than or equal to the x value. So think about like 1.5 is right here. 1.5, the greatest integer less than 1.5 is 1. Let's say you have 1.9 right there. The greatest integer less than 1.9, less than or equal to rather, is 1. But then when you go up here to 2, the greatest integer less than or equal to 2 is 2. So it's a step, and we call it a step function, or the greatest integer function, because it looks like stairs like this. Let's go over here. Let's say negative 0.5. The y value is the greatest integer less than or equal to negative 0.5. Well, the biggest integer that's not greater than negative 0.5 is negative 1. So all the y values here are negative 1. Let's look at, say, negative 1.2. Negative 1.2 is like right here where the cursor is. Now the greatest integer less than or equal to negative 1.2 is negative 2, so all those y values are down here. So it's a nice, what we call step function. Now let's look at the derivative, like it's say at x equals 0. Now clearly it's not continuous at every integer value. At every integer value, it's not continuous, and it turns out it's not going to be differentiable at those points either. Now let's think about those derivatives. If you look at the left-hand derivative and then the right-hand derivative, okay, so f of x minus f of 0, again, 0 is our c value here, over x minus 0. So we get the same expression in both cases, except we're letting the limit go from the left and the right. And let's see what happens. Okay, the limit from the left here is the greatest integer less than x over x. Now let's think about this. As x is getting really close to 0 from the left, what is the greatest integer value going to be? Well, that's a negative number. The greatest integer of a very small negative number, the greatest integer less than a very small negative number is going to be negative 1. So negative 1 divided by really small negative numbers. So negative 1 divided by really small, increasingly small negative numbers, you're going to have negative divided by a really small negative, get a positive infinity. Okay? So that's what the limit ends up being from the left when you look at the step function at x equals 0. Now what about the limit from the right? The limit from the right, what is the greatest integer less than or equal to 0? If you're talking about really small positive numbers. Okay? Well, if you're talking about really small positive numbers, the greatest integer less than or equal to a really small positive number is going to be 0. So you're going to have 0 divided by really small positive numbers. So what's 0 divided by really small positive numbers? It's 0. So notice the left-hand limit does not equal the right-hand limit. So the general two-sided limit that we need to exist does not. Okay, so since the two-sided limit does not exist, that means that the step function is not differentiable at the point 0. And in fact, it's not differentiable nor continuous at any integer value. And this kind of stresses the importance of the link between differentiability and continuity. Okay, if f is differentiable at some point, then it's guaranteed to be continuous at that point. Okay, so differentiability implies continuity, is what we say. Okay, although that is very true, what is not true is the converse. That is, continuity does not imply differentiability. Okay, there's plenty of cases where we're going to have a continuous function, a function that's continuous at some point c, but not differentiable at that point. Now, the prime reasons why that happens is if there's a sharp turn in the function, we call that a cusp a lot of times, or there's a vertical tangent line. Okay, that's when you're going to have these points that are not differentiable, but the function is continuous, like that time where we saw a vertical tangent line a little while ago. Now, let's look at a point. Let's look at a function where this is a prime example of. So you have the absolute value function. It's a v. Now, let's say the absolute value of x minus 2. Okay. Let's just think about this before we look at the actual limits. Let's just think about what a derivative is. The derivative, let's say from the left, is the slope of the curve from the left. And what would you say the slope of the curve from the left is? Well, the slope of this, and not really curve, but the slope of this line is negative 1. The right-hand derivative is this slope from the right, which is positive 1. And those two things, those two lines meet at this point 2, and the slope from the left is not equal to the slope from the right, so it turns out it's not differentiable. We have a very sharp turn here. The derivative at x equal 2 does not exist. Okay? Now, this function is certainly continuous. There's no holes here. There's no gaps. There's no asymptotes. So this is a very continuous function. It is a continuous function at x equal 2, but it's not differentiable because the left-hand limit that is the left-hand derivative and the right-hand derivative, do not match because there's a sharp turn in the graph. Now, let's look at a few limits to see why that is the case. Okay, now, as usually with absolute value, we're going to have to break this apart into cases. Okay, so let's see here. We need to look at the left-hand and right-hand limits. So we have the function f of x equals the absolute value of x minus 2. So what happens at x equal 2? Well, if we want to find the derivative, that is, find the derivative of x equals 2, we would say that these two things have to exist. For f prime at 2 to exist, the following two limits must exist and be equal. We need to look at the limit as x approaches 2 from the right of f of x, so that would be the absolute value of x minus 2 minus f of c, so the absolute value of 2 minus 2 over x minus 2, and the limit as x approaches 2 from the left of the absolute value of x minus 2, f of x minus f of c, so 2 minus 2, over x minus 2. Now, let's see. Those limits are the limit as x approaches 2 from the right of the absolute value of x minus 2 over x minus 2. And this one is equal to the limit as x approaches 2 from, I said the wrong one, right. Let me fix that. Right and 2 from the left. Let's see, absolute value of x minus 2 over x minus 2. Now, we have dealt with this function or a similar function many times this semester, in fact. What does the graph of this look like? Okay, let's see. At x equals 2, let's look at these functions. We have positive 1 there and negative 1 here. Here's what these graphs look like. A horizontal line like that, and a horizontal line like this. Now, why is that true? Now, this function is not defined at x equal 2. That's fine. But what about like at 3, at 4, for numbers to the right of x equals 2? We're going to have, let's say, 3, for instance. 3 minus 2 is 1. Absolute value of 1 is 1. Divided by 3 minus 2, which is 1. So you have 1 divided by 1. What about 5? If x equals 5. 5 minus 2 is 3. Absolute value is 3. Absolute value of 3 is 3. Divided by 5 minus 2 is 3. So 3 over 3 is 1. So for any value to the right of 2, the solution, the expression, always reduces to a 1. What about for any value less than 2? Let's say pick negative 3. Okay? At negative 3, you're going to have negative 3 minus negative 2 is negative 5. Absolute value of negative 5 is positive 5. On the denominator, though, you would have negative 3 minus 2, which would be negative 5. So you have negative 5, the quotient of 5 and negative 5, which is negative 1. Okay? At x equals 0, you'd have 0 minus 2. The absolute value of 0 minus 2 is positive 2 over negative 2. So positive 2 over negative 2 is negative 1. So the values for any number less than 2, the x value less than 2, this is going to give you a negative 1. So we would say that's positive 1, and that is negative 1. So the limit from the left is not equal to the limit from the right. Thus, the limit as x approaches c of f of x minus f of c over x minus c does not exist. Because these two don't match up, the general two-sided limit does not exist. Okay? Since that does not exist, that means the derivative does not exist. And the derivative does not exist, as we talked about before, because if you think about what's happening with absolute value, if you have a 2 there, you have a v like this, where if you look at remember that what the derivative is. The derivative is the slope of the tangent line. The slope of the tangent line, and for a linear equation, it's going to be just the slope of the line. So the slope of the line to the left of 2 is -1, but the slope of the line to the right of 2 is 1. So those two slopes do not match up when you get to the point at 2. Now, that's not to say that the derivative at x equal 1 does not exist. The derivative at 1 does exist. The derivative at 3 exists. It's just that the derivative at that cusp does not exist. So the derivative at x equal 2 does not exist. However, this function is differentiable everywhere else. 2 is the only sharp turn in the absolute value graph. There will be functions where there's lots of sharp turns. And so there'll be points where they're not differentiable, or for maybe there'll be other reasons why there's not differentiable points. But as for this particular example, the only sharp turn is right here at x equal 2, and so it's not differentiable at that point. Again, why are we doing this? We're doing this to show that function is continuous at x equal 2, but it's not differentiable at x equal 2. So continuity does not necessarily imply differentiability. All right, so just to sum up, we have a relationship, a very important relationship between continuity and differentiability. That is, if a function is differentiable at some point c, then it's guaranteed to be continuous. That is, differentiability implies continuity. However, it is possible for a function to be continuous, like we just saw, but not be differentiable at a certain point. So like the cube root of x, we saw that. Or we saw the absolute value of x. There's lots of examples of a function that happens to be continuous at a point, but has a cusp or a vertical tangent line or a sharp turn that means that it's not differentiable at a specific point. It might be differentiable at other points, but not necessarily differentiable at that specific point where that sharp turn occurs. Okay? If a function is not continuous at c, then it's not differentiable. So let's say you have a hole in the graph, or a function that for whatever reason is not continuous. There's a gap or something like that. All those reasons we talked about in the previous chapter. If it's not continuous, then it's not differentiable. Because not continuous means there's going to be a problem with the limits, and derivatives are based on limits. So not differentiable implies, not continuous implies not differentiable. So 3 points to really commit to memory, to really let sink in, think about it. Just think about that relationship between differentiability and continuity, because this relationship will be talked about, will be discussed throughout the rest of the semester. If you have any questions, feel free to always ask, and I hope this has been helpful. And we'll pick up next time with section 3.2.